Welcome back. Today we're going to cover Chapter 5, Sensation and Perception. Sensation, the biological process of detecting physical stimuli. It's not to be confused with feelings, or Beyonce, or that tingling in your leg from sitting too long. No, this is sensation, the process by which your body says, hey, something's happening, before your brain even decides if it's worth caring about. Sensation is the detection of external stimuli. We're talking light hitting your retina, sound waves bouncing into your ear, chemicals swirling around your tongue, pressure on your skin. Your sensory receptors convert these stimuli into neural impulses, which your brain then uses to possibly build a coherent experience. Or not, your brain can be moody. Let's meet the cast. Photoreceptors, mechanoreceptors, chemoreceptors, thermoreceptors, hot and cold feelings on your skin, nociceptors, pain detectors also known as ouch processors. All of these are basically sensory interns, reporting everything to the brain, whether it's useful or not. Sensation only works because of transduction, the magical conversion of external energy into electrochemical signals. Without it, light is just light, sound is just air wiggling, and you're just standing in the field going, huh? Absolute threshold is the bare minimum a sense needs to notice something. Psst, did you hear that? No? Well, that's probably because it was below your absolute threshold. Which brings us to today's question. What's the quietest, faintest, dimmest, softest thing you can actually detect? Welcome to the elusive world of the absolute threshold. It's also known as your sensory system's minimum effort policy. Technically, the absolute threshold is the lowest level of a stimulus you can detect 50% of the time. Not 100%, that'd be too easy. Your senses are moody. So scientists said, fine, if you noticed it at least half the time, we'll count it. Examples: seeing a candle flame 30 miles away on a clear night, hearing a watch tick 20 feet away in a quiet room, feeling a bee's wing drop on your cheek from 1 centimeter above, tasting 1 teaspoon of sugar in 2 gallons of water, smelling 1 drop of perfume in a 3-room apartment. These thresholds are the biological equivalent of asking, can you maybe detect this tiny thing if the wind is right and Mercury isn't in retrograde? This matters because your brain needs a cutoff. If it responded to every whisper of input, you'd be curled up in a sensory overload burrito right now. It's like a doorman. Too faint? No thanks. You're not on the list. Your senses are working even when you don't think they are, but they draw the line somewhere. That line, it's the absolute threshold. And let's be real, it's not absolute. It changes. Mood, fatigue, age, attention, they all mess with it. The difference threshold, because your brain doesn't just need to know something's there, it wants to know if it changed. Just noticeable is a cell phone lighting up in a dark movie theater. You're going to notice it more than if you saw it in a brightly lit shopping mall. That's the just noticeable difference. It's important to note that sensation does not equal perception. And this is the part that a lot of students will mix up. Sensation, a light wave hit your eye. Perception, oh, that's my ex's car. Panic. Sensation is passive. Perception is interpretive. Sensation is the data. Perception is the drama. Sensation first, interpretation second. Start with the raw data. Your sensory receptors pick up info from the environment. It can be light, sound, touch, and then it sends it to your brain. Your brain says, I now have enough clues to figure this out. Example could be doing a puzzle with the box cover. You already think you know what you're looking for. You glance quickly at a blurry street sign, but your brain autofills what it likely says based on your memory of the area. Or if you read TH3QU1CK BR0WN F0X and your brain fixes the nonsense. The quick brown fox. Why it matters? Your perception is not purely objective. Your brain constantly guesses, and sometimes it gets it hilariously wrong. Understanding this explains illusions, misheard lyrics, and why you thought your ex changed, but absolutely did not. Bottom up is sensation first, brain second. Top down is brain first, sensation second. Bottom up is more likely when something is new, strange, or unfamiliar. Top down kicks in when you're rushed, tired, or overconfident. So maybe finals week. Here you can see top-down processing occurs when previous experience and expectations are first used to recognize a stimuli. Bottom-up occurs when we sense basic features of stimuli and then we integrate them. Factors affecting perception. Because your brain doesn't just passively receive reality like a Netflix stream. No, it edits, filters, guesses, and sometimes just full-on makes stuff up. Let's dive into the main perception warpers that decide whether you're seeing facts, fiction, or a third option powered by caffeine and unresolved childhood memories. Attention. Perception starts with what you pay attention to. Your brain is bombarded with sensory input 24/7 and has the audacity to ignore most of it. If you're distracted, overwhelmed, or daydreaming about chicken nuggets, yeah, you're probably not perceiving things accurately. Example, if you ever looked someone in the face and not realize they changed their hairstyle, yep, you were too busy perceiving your own existential dread. Past experiences is the second one. If a dog bites you as a kid, even a chihuahua in a tutu might look like a threat. 3, culture. Culture influences what we notice. In some cultures, a smile can signal discomfort instead of happiness. 4, expectations. If you're told to expect a friendly, helpful person, you overlook the fact that Bob has the personality of a damp sponge. 5, motivation and emotions. Translation, your brain wears whatever emotional glasses you've got on, and sometimes they're cracked. Context. The environment shapes perception. A loud bang in a concert, cool pyrotechnics. A loud bang in a library, instant cardiac event. And lastly, biological factors. Brain status equals perception status. Vision issues, hearing loss, neural damage can all perceive with how you see the world. Perception isn't reality. It's your brain's best guess at reality, heavily influenced by your past, your present, your mood, your culture, your eyesight, and your deeply held belief that your cat understands English. The molar-liar illusion is that little mind prank where 2 lines of the exact same length look wildly different, all because someone slapped some arrowheads on the ends. It's like your brain being gaslit by geometry. Both lines are the same length. Your brain says, LOL, no they aren't. You say, I have trust issues now. It's all about perceptual context and depth cues. The inward pointing arrows make the line look shorter. The outward pointing arrows make the line look longer. Your brain interprets the arrowheads as cues for depth or perspective, like the corners of a room or building. Basically, your visual system is trying to apply 3D rules to a 2D drawing, and it backfires hilariously. Cognitive explanation is that the top-down processing, your brain uses prior knowledge to interpret what you see. Size constancy, your brain adjusts for perceived depth and distance even when it's not needed. It's the visual equivalent of someone trying to be helpful and just confuse everything. Fun fact, people from non-industrialized cultures are less likely to fall for the illusion. In other words, if you grew up around huts, curves, or nature, you might be immune to this nonsense. This matters because it shows that perception does not equal reality. It's a textbook case of visual illusion and how our brains construct reality. And it proves your eyeballs can't always be trusted, especially when they've been hanging out with your assumptions. We will talk about amplitude and wavelength when we discuss in further detail visual and auditory stimuli. They both occur in the form of waves, and some of the properties are amplitude and wavelength. Amplitude, or the height of a wave, is measured from the peak to the trough. It's measured from peak to peak. Frequency is the concept that's everywhere from sound waves to your overly chatty group texts. It most often pops up when we're talking about sound. Light is a wave, also a particle, also a scam, depending on who you ask. Let's talk about waves. Wavelength is the distance from one peak of the wave to the next, how long it takes light to say hi again. Amplitude is how tall the wave is. Big wave, bright light, small wave, mood lighting. Frequency is how often the wave hits per second. High frequency equals more energy, which equals blue light. Low frequency equals less energy, which equals red light. You can see most electromagnetic waves. Your eyes are picky and only respond to a narrow band, what we call the visible spectrum. Everything else, like X-rays and gamma rays, is light your eyes can't RSVP to. So you think you're seeing color. That's cute. Color is your brain's interpretation of different wavelengths. Short wavelengths equal blues and purples. Long wavelengths equals reds. Middle ground, the greens that scream nature in every eco-themed commercial. But the color doesn't exist out there. You're just perceiving the bounce pattern of photons and assigning them to Crayola boxes. Honestly, it's impressive and deeply delusional. Now swap your eyeballs for eardrums. Sound waves are mechanical. They need a medium, like air, water, or awkward silence at dinner. Amplitude equals loudness. Bigger the wave, louder the sound. Frequency equals pitch. High frequency equals squeaky. Low equals very white. Your brain turns these compressions into language, music, and unfortunately TikTok trends. And yes, it's the same frequency or amplitude deal as light, just in a more vibey, head-bobbing context. So that's waves, wiggling through space, tricking your senses, and somehow delivering color, light, and noise into your skull. Not bad for something that doesn't even have a body. And this figure illustrates the loudness of some common sounds. So on one end, the hearing threshold is 0. On the other end, 140 decibels is harmful. Now we're moving on to vision. Light enters through the cornea, the eye's transparent dome. It's like the windshield of your car, if your car could cry. Then it squeezes through the pupil, which is just a hole, literally. A stylish iris-framed hole that expands and contracts depending on how dramatic the lighting is. Next stop, the lens, which focuses light onto the retina. Unless, of course, you're me and your lens is cooperative as a cat in a bathtub. Hello, glasses. And here are all of the different areas of the brain, which as you can see is quite detailed. Now here's where the magic happens, or the lies begin, in your photoreceptors. The retina holds two kinds of photoreceptors. Rods equal night vision, grayscale, and motion, like black and white CCTV. The cones equal color, detail, and daytime clarity, your personal 4K sensor. Rods equal quantity, cones equal quality, and both equal confusion when your brain tries to stitch it all together. Here's a visual of the photoreceptors as well, in the different parts and how it works. The optic chiasm. From the retina, signals travel down the optic nerve to the optic chiasm, a nerve swap meet where half the fibers cross the other side of your brain. That means your left field of vision is processed by your right hemisphere, and your right field of vision is processed by your left hemisphere, because your brain just can't do anything the simple way. Finally, everything lands in your visual cortex, tucked in the back of your brain in the occipital lobe, because who doesn't want to process sight with the part of the brain furthest from the eyes? The cortex decodes signals into objects, shapes, movement, and meaning, all in milliseconds. Your brain, underpaid, overworked, and still more accurate than WebMD. Color vision, the drama between theories. There are two main theories for how you see color. Trichromatic theory, red, green, and blue cones mix to make all the colors, like the RGB setting on your monitor. Opponent process theory, pairs of colors compete. Red versus green, blue versus yellow, black versus white. The second theory explains after images. Stare at something green long enough, and when you look away, you'll see red, because your brain is petty and overcompensates. Stare at the white dot for 30 to 60 seconds, and then move your eyes to a blank piece of white paper. What do you see? The after image is the continuation of a visual sensation after removal of the stimulus. Depth and patterns, or as your brain calls it, guesswork, but with style. So how do you know that a tree that is far away is really far away and not just a really tiny tree? Depth perception, your brain's magic trick to make 2D retinal images look 3D. Binocular cues is using both eyes, like retinal disparity, the difference between what each eye sees. Your brain uses this to build 3D vision, like a sculptor with two chisels. Monocular cues are stuff you can pick up with one eye, including linear perspective, parallel lines converging, interposition, objects blocking others are closer, relative size, bigger equals closer, usually, texture gradient, stuff gets blurrier the farther away it is. Your brain basically fakes depth like a Pixar movie animator. Sometimes one or more types of cones don't work correctly. That's color blindness. Most common is red-green, which means Christmas decorations become an abstract guessing game. It's genetic, more common in men, and makes playing Uno a lot more stressful. Your visual system, a bunch of light-sensitive cells, a dramatic nerve crossover, and a brain doing its best to interpret it all before your next blink. Now we're moving on to hearing, or your auditory system. The ear is divided into three divisions: outer, middle, and inner. Outer ear catches sounds like a weird flesh funnel. Middle ear is full of bones smaller than your pinky nail. Inner ear, the real MVP, full of fluid, hair cells, and drama. Here's the journey. Sound waves get caught by your pinna or your ear flap. They travel through the auditory canal and hit the eardrum or tympanic membrane, which starts to vibrate. These vibrations go through three bones, the malleus, incus, and stapes, also known as the hammer, anvil, and stirrup. Blacksmith much? Finally, the stirrup taps on the oval window of the cochlea and unleashes the wave party. And here's a visual of some of those parts and others that make up the auditory system. Auditory transduction, hair cells, and Hippies waves. The cochlea is a spiral-shaped structure filled with fluid and lined with hair cells. Not actual hairs, but tiny receptor cells that bend when waves pass. These hair cells convert mechanical movement into electrical signals that your brain can interpret as "that's my jam" or "please make it stop." Your brain figures out pitch based on frequency theory, how fast the hair cells fire, and place theory, which part of the cochlea wiggles. High frequencies vibrate the base, low ones vibrate the tip. Your cochlea is basically a stretched out piano inside your head. Both theories explain different aspects of pitch perception. The rate of action potentials applies up to about 4,000 Hz, but higher frequencies can only be encoded using place cues. Sound localization, how you know the boom came from behind you. Your two ears are spaced apart for a reason, stereo sound. Your brain uses interaural time differences and intensity to figure out where a sound is coming from. If a sound hits your left ear just a smidge earlier and louder than the right, your brain says it's on the left. Duck. Evolution. We love it. Hearing loss. When the party gets too loud. There are two major kinds of hearing loss. Conductive is issues in the outer or middle ear. Eardrum damage, earwax conspiracy, tiny bone rebellion. Sensory neural is damage to hair cells or auditory nerves, often permanent, usually thanks to rock concerts or bad luck in the genetic lottery. Good news, hearing aids and cochlear implants can help because science is cooler than ever. Gustation and olfaction are also known as taste and smell. They work so closely together, they're basically the sensory version of a buddy cop movie. One's a chemical sniffing hotshot, the other just wants to know if it's spicy. Taste, or gustation, not just sweet and sour. Your tongue is covered in little bumps called papillae, and inside those are taste buds, the flavor detectives of the mouth. You've probably heard of the 5 basic tastes: sweet, sugar, and the promise of dopamine. Salty, electrolyte cravings. Sour, this might be poison, but let's risk it. Bitter, definitely poison, probably kale. Umami, the savory chef's kiss taste found in meat broth and overpriced ramen. Each taste bud contains receptor cells that respond to one or more of these flavors. And no, your tongue does not have a special map where each section only detects one taste. That's a myth. Burn it with your unseasoned chicken. Here's a visual of your taste buds and the individual taste receptor cells. And then B, it's showing it close up of the tongue surface. Smell, olfaction, the nose knows. Smell is where things get weird. Odor molecules float into your nasal cavity where they bind to receptors on your olfactory epithelium. These signals go straight to the olfactory bulb and then into the limbic system, the part of your brain that handles emotion and memory. Yes, your nose has a direct hotline to your feelings. That's why one whiff of grandma's cookies and you're 7 years old again crying over a Lego injury. Unlike other senses, smell doesn't go through the thalamus first. It's raw, it's emotional, it's drama. Flavor isn't taste, it's a full-on collab between your mouth, nose, texture sensors, and expectations. Ever try eating while holding your nose? Suddenly a jelly bean could be a crayon. 80% of what you taste is actually smell, which means if you have a cold, your lasagna tastes like cardboard regret. Your tongue and nose have been conspiring to manipulate your food choices your whole life. And honestly, they're doing a great job. Touch, the original social network. Because your skin isn't just there to keep your insides from falling out, it's also your first responder to pain, temperature, pressure, and existential dread. Let's start with mechanoreceptors, the skin's pressure sensors. They're like over-caffeinated interns reporting everything from a mosquito landing on your arm to the crushing betrayal of a too firm handshake. You've got Meissner's corpuscles, which are light touch, friendly pats, and awkward shoulder brushes. Pacinian corpuscles are deep pressure, massage chairs, bear hugs. Merkel's discs, texture and fine detail, reading, braille, filling the lint in your pocket. Ruffini endings, stretch and sustained pressure, like when you lean into your regrets. Here's a visual of your skin surface and the different areas that we just talked about. Thermoception is feeling hot or not. This one's simple. You have specialized receptors for warm and cold. They don't measure actual temperature, they sense changes. That's why jumping into a cold pool feels like betrayal, and then suddenly refreshment. Thermoreceptors are the mood ring of your sensory system, not always accurate, but very dramatic. Nociception is also known as pain, but make it scientific. Nociceptors are your pain detectors. They're not just warning bells, they're fire alarms with feelings. There are different types. Thermal nociceptors are fire and frostbite edition. Mechanical nociceptors are stub toes and paper cuts. Chemical nociceptors are chili pepper regrets and acid burns. Pain is not just about tissue damage. It's your brain deciding whether something is important enough to whine about it, which explains why you didn't notice that paper cut until somebody pointed it out. Pain perception. It's all in your head, literally. Pain is personal. Your brain filters it through experience, mood, distraction, and context. Gate control theory says you can't distract your brain from pain by activating other touch pathways. That's why rubbing your elbow after hitting it sort of helps. Emotions influence pain too. Anxiety amplifies it. Laughing dulls it. Ice cream heals all. Pain is subjective, manipulative, and a total drama queen. Respect it, but don't trust it completely. Today's theme, vestibular sense, balance and body awareness. Two senses you didn't know you had until you trip over absolutely nothing. It's deep in your inner ear that lies the vestibular system, your personal gravity detector. It's made of semicircular canals, 3 fluid-filled loops that detect rotation, like if your head spins left, right, or out of control. Otolith organs, the utricle and saccule, which detect linear acceleration and head tilt. How does it work? As you move, fluid sloshes around. Tiny hair cells inside get pushed and bent, sending messages to your brain like, whoa, we're falling, or the room is spinning. That second one might also be tequila. Here's a visual of the vestibular sense. The maculae are specialized for sensing linear acceleration. Proprioception, the sense that says I know where my elbow is. Proprioception is your body's internal GPS. Without it, you couldn't touch your nose with your eyes closed, or walk without looking at your feet, or dance like no one's watching, because you'd probably fall over. Your joints, muscles, and tendons constantly send signals to your brain saying, hey, arm here, leg bent, butt still seated. It's like having an annoying roommate who narrates your every move. And thank goodness they do. Kinesthesia is your movement vibe check. If proprioception is position, then kinesthesia is motion. It's your sense of how your body is moving and how fast. It helps you adjust when you toss a ball, swing a bat, or dramatically fall onto a couch after work. It's mostly subconscious, but absolutely essential, especially if you're planning on walking, dancing, or faking a feint. Gestalt, when your brain gets creative. Let's recap. Gestalt psychology taught us that your brain is not a passive receiver of sensory data. It's a hyperactive intern trying to organize everything with zero context. So it sees proximity and assumes grouping. It sees similarity and assumes connection. It sees lines continuing and assumes destiny. It sees incomplete figures and draws them in anyway, because your brain hates ambiguity. That brings us to implicit bias. Implicit bias is when perception becomes prejudice. Your brain doesn't just complete shapes, it completes people too. Implicit bias is the set of unconscious attitudes and stereotypes that affect how you interpret others without realizing it. That means two people do the same thing, your brain might judge them differently. Why does this happen? Because your brain loves shortcuts. It learns patterns from experience, media, culture, and childhood chaos. Unfortunately, those same patterns can lead to snap judgments, microaggression, and a full-on oops, I'm the problem moment. And since perception is the first step in all of this, it means what you see, what you focus on, and what you expect to see all get filtered through this bias. Bias isn't your fault, but it is your responsibility. Awareness is the first step. Your brain wants to make sense of the world. It wants patterns. It wants closure. But sometimes what it really needs is a reality check. So here, what do you see? The figure is the focus of the visual field. The ground is the background. Our perception varies depending on what we view as a figure and what we view as the ground. The Gestalt principle of proximity suggests that you see one block of dots on the left side and 3 columns on the right. Principle of similarity. When looking at this array, we likely perceive alternating rows of colors. Continuity would suggest that we are more likely to perceive this as 2 overlapping lines rather than 4 lines meeting in the center. Closure suggests that we will perceive a complete circle and rectangle rather than a series of segments. One more illusion, duck or rabbit. What do you see? Visual illusions, also when your senses go rogue and your brain just nods like, yep, that's real. Spoiler, it's not. And as discussed previously, implicit bias is based on our experience and our history. And it can influence us in the wrong direction and make us make snap judgments that are incorrect. Goff's research showed that black boys are considered more responsible than white boys of the same age. So what does this say about law enforcement education and jury perception of defendants of different races? That's all for Chapter 5. See you next time.